we're going to be looking at some practice problems. So in the same way that with controllability we had a number of properties that were all interrelated, so with observability we have a lot of the same things going around here. We have the observability matrix instead of the controllability matrix. We have the observability Gramian. We have the null space of the the output map. So we have the eigenvalue placement. We have block triangularizing transformation, unobservable modes. We have the PHR test, and so forth. So we have all of these same kinds of things for observability as we did for controllability. Well, here's an example. I have this system, and notice in this case I don't even bother to have an input because I'm only concerned with the observability. Here's my output y, and so for some initial condition, again with no input, I get this sequence of values coming out. Okay, so this sequence of values. And so the question is, what was the initial condition, given that these were the output values? So we go through and we form our observability map. Okay, in this case we're going up to 3 terms, and this is what we get. So this is C times A squared. And when we calculate the determinant of this, we get -8. That's non-zero. Therefore, our system is observable. And so we look at the output then. To find the initial condition, we basically would have this condition. X of 0 is equal to the observability map inverse. Notice in general, this matrix may not even be square, so we wouldn't necessarily be able to take the inverse, but we should be able to have a left inverse of it, times the vector of output values. And when we compute that, we actually get these values. So this is the obtaining of the initial condition from the output values. We picked enough output values. In this case, we only needed 3 because our system was 3rd order. And so but with 3, this matrix was invertible, and so we could obtain this. Now, we could also have gone, if we had one more value, we could have gone through and worked with it, in which case this matrix would no longer have been square. It would have been a taller matrix, and we would use the pseudo-inverse instead of the inverse, and that would still have worked. Second example, I have this system which has the same A matrix. The C matrix has changed a little bit. Again, we have these values, this sequence of values, and it's a little bit different than the sequence we had last time. We have this sequence of values, and so the question is, what was the initial condition? So we look at the observability map, and we find that so this column is the same as that column, and so we have, or this row is twice this row. So we have that the observability map is singular. Therefore, we cannot uniquely obtain what the initial condition must have been. So because this matrix is singular, there is a non-trivial null space, and so here's the vector in the null space. And so we can show that both this initial condition and this initial condition give the same output sequence, the desired output sequence that we were given. So clearly these are not unique vectors, so this shows, and actually the difference between these two vectors is in fact a multiple of that. So if we now take the system and put it into modal coordinates, okay, if we take this system, put it into modal coordinates, here's my eigenvector matrix. I put it into modal coordinates and I get this, and so I can see that here I have a column of zeros. So this is diagonal 0, 1, 2. I have a column of zeros. So this column of zeros tells me my system is not observable. Okay? So with the controllability, we had to worry about rows of the B matrix. For C, we have to look at columns of 0. So this is a 0 element. Therefore, this is an unobservable mode. Okay? And because this is not 0, this is an observable mode, and this is also an observable mode. And so we can in the modal coordinates, we can exactly see the observable modes and unobservable modes. Suppose now we had a triangularizing transformation. So here's a T. So instead of just doing the diagonal form, we used a triangularizing transformation. So this T that somehow I magically came up with puts the system into this form. Okay, so this is, it's triangular. So here's a 1x1 block. Here's a 2x2 block. And so I can see that this doesn't tell me, I have no columns of 0 in there. So this doesn't tell us anything about observability. So not every triangularizing transformation tells us something about observability or controllability, as we saw with controllability. So here's a slightly different triangularizing transformation. When we use this is what we get for the system. And now I have this block is paired up with that column of zeros. And so this triangularizing transformation proves that the system is not observable. So if I look at this A matrix compared to the previous A matrix, notice that this block is exactly the same as what we had in the other case, and this is exactly the same. Okay, but so the difference in the triangularizing transformation then is it's clear that not every triangularizing transformation would prove unobservability, and so it's not a particularly effective means of showing unobservability, but it comes in handy in some proofs. So here's our third example, and in this case we can actually work with our system matrix. Our system matrix has A, B, C, D matrices in it. So here's A, B, C, and D. So rather than, and notice here I have it in discrete time, but I could just as easily have it in continuous time. So a lot of these things, even though we're listing them in discrete time, really have their counterparts in continuous time as well. All right, so this is the system that we have. Now, if I actually go through and compute the transfer function for this system, so here's the transfer function D, which is this, plus C, Zi minus A inverse B. When we actually apply this and the smoke clears, here's what we end up with. It simplifies a lot. There's a lot of cancellations going on. Notice that this is a fifth order system, which means it should have 5 poles. But notice that this system only has 2 poles in the transfer function, which means somehow or other 3 poles go away. Okay, so there's something going on here. So the similarity transformation, I can put it into this form. I can put it into the similarity transformation form of the system matrix this way by taking this times the system matrix times that transformation inverse. Okay, and so in order to put it into modal form, I have V. Here's my eigenvector matrix for this system. T is the eigenvector matrix inverse. Okay, and so when we actually put it into modal coordinates, this is the new S bar that I get. And so now here I can see this is diagonal. In this case, I'm able to get a diagonal form. And now in terms of controllability, I can see rows of 0. Okay, and I can see columns of 0. Okay, so every column of 0 in the new C matrix corresponds to unobservability of that mode. So this is observable, that's observable, these two are not observable. Okay, so that guy and that guy are unobservable modes. For controllability, every row of 0 is an uncontrollable mode. So this one is controllable, this one is controllable. These 3 are not controllable. Okay, so this guy, and this guy. And so all that leaves left in our transfer function is exactly those 2 eigenvalues, those 2 poles. Okay, so we can see exactly, at least in the modal form, where the uncontrollability, unobservability is happening. So that's what we have, and so in many ways the common decomposition is helpful, but really the modal form I find to be a lot more. Well, it's helpful in some ways. Okay, that is, if I can actually diagonalize my system, then that's great. Also, sometimes when you do these kinds of calculations, you'll get like very, very small numbers, 10 to the minus 15. that generally is considered to be 0. Okay, it's within machine, it's close to machine precision, and so you need to look at those kinds of values. But this then is one way of examining this is actually a Kalman, this is a form of the Kalman decomposition, but to me this is more instructive than just the standard form where you have all the different other blocks mixed up in there, non-zero. So this is observability and the Kalman decomposition.